Hey folks, today is Thursday the 19th. This is coming for Friday the 20th lecture. At the very end, I'll do a real quick review of what the homework's going to be that's due next Wednesday. It's the last sheet of the PDF. You don't have to listen to me talk about it, but I will. So if you want to skip ahead of that part, you can. All right. Actually, strike that. I'll just make it a separate video. How about that? Anyway, so here we go. We're talking about Fourier series, and this is going to be a continuation of what we were doing in class on Wednesday the 18th. So we'll start off with a review as we always do. Fourier series, I have a function that's periodic, f of x periodic with period L, meaning that f of x is equal to f of x plus L for all x. I'm going to try to write f of x as a sum of sines and cosines. And so I have a naught plus then the summation here, and you're probably well acquainted with that. And in this particular case, this works because f is periodic with a period of 2 pi. And then later on, we'll talk about other periods when we use those. And so these are the formulas we can use to find the Fourier coefficients. So here is my example from class. F of x is equal to 1 over 2 pi x plus a half. And then that repeats every 2 pi. So it looks like that, and you can connect these little dots here and make it look like a sawtooth. It's called a sawtooth wave. There's many different forms of it. This is the one we're doing here. All right, so we started out finding a naught. That's the average value. Looking at this, it starts from 0, goes up to 1. It's a linear function. It sure seems like the average should be a half. And then here's just some straightforward integration, gives you a half. That's the average value. Check. It works well. All right. And then we did this in class yesterday, but we're going to just go ahead and run through it real quick again. A sub n is 1 over pi integral from negative pi to pi of my f of x times cosine of nx. And I did the integration by parts differently in class. On further reflection, this is probably a little bit simpler. Instead of splitting things up and doing lots of integration, let's just take that whole function f of x and call that my u. So u is 1 over 2 pi x plus a half, and du is just 1 over 2 pi. And then the dv is the same as before. dv is cosine of nx. v is 1 over n sine of nx. All right, and so now I'm going to take the 1 over pi that comes up front times big brackets. This is now replacing the integral. U times v, here's my function times the v. And then I evaluate it likewise, minus the integral of v du. All right, I kind of crammed some stuff in there, forgot the 1 over n. So that's the v du part. All right, now this part here in red, you can see that is going to go to 0 because it ends in integer. So sine of multiples of pi, it will be 0. So I have 0 minus 0, that just goes away. And I'm left with integrate this side over here. Antiderivative of sine gives you negative cosine, and plus this negative sign here puts a positive sign up front here. 1 over 2 pi n squared, cosine of nx, evaluated from pi to negative pi. And then when we plug that in, I have cosine of n pi minus cosine of negative n pi. Remember, cosine is an even function. So cosine of a negative angle is the same thing as the cosine of the angle. So that's the same number subtracted gives me 0. So that all of the an's are 0. Okay, that's where we left off in class. And then we kind of burned through this part quickly and we jumped to mathematics and whatnot, but I'll just walk you through it again because integration by parts is not terrible. Let's just remind ourselves how it works. B sub n is the same as before, but instead I have sine instead of cosine. All right, and then we write it out. And again, integration by parts, same kind of thing, but notice there's a minus sign right out here because antiderivative of sine is negative cosine this time. And so now 1 over pi, here is the u times v evaluated from negative pi to pi minus the integral of v du, and here's that minus sign from this minus sign right there. All right, so now plug in pi into here. Like last time, this whole thing went to 0. It's not going to happen this time. You plug in pi, and I get a 1/2 plus a 1/2. Plug in pi, I get negative 1 over n cosine of n pi minus, now plug in negative pi into here, and I get negative 1/2 plus a half. That does give me 0. Since this whole thing is 0 multiplied by this whole part here is 0. Okay, so this is all 0, this is not 0, and this Antiderivative cosine is a sine. I'll plug in pi's again, and I'm back to 0 again. So now this is the only part that's left over. Half plus a half is a 1 times a negative 1 over n times a pi gives me a negative 1 over n pi, cosine of n pi. Now when n is even, cosine of n pi is 1. So I have this negative out front here, right? So I get negative 1, and when n is odd, I get a positive 1. That gives me this thing here, and I can rewrite this whole thing as b to the n, or b sub n is, I think I wrote b to the n, sorry. B sub n is negative 1 to the n plus 1 over n pi. Okay? Then we look back at our graph, and we can say, this is what we talked about in class yesterday, but still sort of a review. I found all my a sub n's were 0, b sub n's were not necessarily 0. I don't think any of them are actually. And so then I'm thinking, oh wait, I'm only using sines, no cosines. So I would expect to see an odd function, but that function there is not odd, except we realize, oh, this is shifted up by a half. If I were to shift all those lines down by a half, I would have an odd function. So what my final answer is I have a function that is a shifted odd function. All right, and then we can graph that quickly. I'll jump over here to Mathematica. And so here is my sawtooth wave. I can integrate, and I get these things here. And I'll just show you, I can simplify this expression, and now it gets cut off, but here's the, I'm making a little ordered pair. Here's the first integral, here's the second integral, and then I'm with Mathematica, can't do this with MATLAB. With Mathematica, I can say the assumptions are that n is an integer. And when I make that assumption, Mathematica says, well, then all of this sine stuff here just goes to 0, because sine of integral multiples, integer multiples of pi are 0. So it gives me 0 here. And then all of this stuff here goes to negative 1 to the n plus 1 over n pi, which is what we had in our notes. And then I can graph them. And I graph the first 10 of this. I get something that looks okay. Let's just try doing just one of them. But I am bothered by the fact that it's too low. And then I look at the formula here. When I did my Fourier, I forgot to add a half. So now I can take my odd function and shift it up by a half, and now that looks better. And then I can do this for, oops, first 2, and then keep on going, 3, and then I think we were up to 10 already in the, when I first started, and so forth. You can see it happening farther and farther. Let's just go up to, let's go up to 20 for kicks. All right, and then once again, we have this jump up there. It's that Gibbs phenomenon where you sort of overshoot stuff when you have a discontinuous function. All right. So that's example number 1, which is kind of a review of example from class before. It ties that all up. All right, so now let's do another example, another sawtooth wave. Okay, this one here, instead of being discontinuous, is continuous. This goes up and down over and over again. And what we have is the function is x when x is positive, negative x when x is negative, on the interval from negative pi to pi. So it kind of defines this little V shape here. And then this part says, now take that little V shape and repeat it every 2 pi, and you get that sawtooth function. Looking at this, I have the question for us. Is this an even function? Is it an odd function? Neither. Think about it. We'll talk about it in a little bit. So a sub 0, let's find the average value. I can stare at this, and it goes from 0 up to pi, 0 up to pi. The average is probably pi over 2. All right, so 1 over 2 pi, negative pi to pi of f of x. And now since I have a piecewise defined function, I need to do 2 integrals. The first integral is from negative pi to 0 of negative x. It's giving the area under this curve, plus the area under this curve. And an argument from just staring at it tells me they should be the same numbers. And as I go through it all, I end up with 1 over 2 pi, pi squared over 2, plus pi squared over 2. Simplify, I get pi over 2. Sure enough, the average value is half of pi. All right, so now let's get the a sub n's. 1 over pi integral from negative pi to pi of f of x cosine nx. And again, I need to split up into 2 different integrals because I have this piecewise defined function. Negative pi to 0 of negative x cosine nx, and 0 to pi of positive x cosine nx dx. Okay, so now one thing I'm going to notice is that in both of these situations, I'm basically integrating x cosine of nx. This has a minus sign out front, but basically the same integration by parts. So u could be x, du is dx, nice and straightforward. dv is cosine nx, which means v is 1 over n sine of nx. And then I got things kind of crammed in here. I should have started this line a little lower down, but 1 over pi comes up front, big brackets. Now this integral here is rewritten here. Now the integration by parts says u times v, x over n sine of nx. But there's this minus sign right here, so that carries up front. And then integration by parts says u times v minus v du. So minus, oh, but wait, I had that minus sign up front. That minus sign turns into a positive here, minus v du. I have this. Plus, and then this is this integral down here. I ran out of space. This is the integral of u times v, and then minus integral of v du. All right, and so then you can see that these integrands are the same here, except the bounds of integration are different. And in both of these cases here, I'm doing integration by parts. Those are just 0, again, because it's sine of multiples of pi. So I'm left with 1 over pi still. And then this integrand here, integrated. Sine of nx has an antiderivative of negative cosine nx divided by n. So now I have a 1 over n squared, evaluated from negative pi to pi. And then the same integrand from 0 to pi. Now this had a minus sign here, so when I integrated, that turns into a plus sign. So this is like a bookkeeping thing, really, right? Just making sure we put all the things in the right places. All right, and now we have, to evaluate this, plug in 0, plug in negative pi, plug in 0, plug in negative pi. For this integral, plug in pi, and then plug in 0. And then I have 2 of these cosine of pi n's. This sign doesn't matter, divided by n squared. I pull the n squared out. And I also have 2 of these minus 1 over n squared. So I pull out the 1 over n squared, and then I have 2 cosine of pi n minus 2. When n is even, that's 0. When n is odd, I get negative 4 over n squared. So you can write it this way, or you can get clever and write it this way. Because cosine of n pi kind of acts like negative 1 to the n. It's kind of the idea. All right. So that's the second example. And now let's just go see what it looks like. So here's our other sawtooth wave. I can redefine my function. Looks like Christmas trees from that point. And then I can integrate with Mathematica. And notice that the second one is all 0. I forgot, apparently, to integrate the part B. This is goofy. I forgot to do the B sub n, and now this is where I come back up here. I meant to write this down. I expected all the B sub n's to be 0. I thought I had written down, but I guess I didn't. All right, now I'm not going to fix it. So I thought, anyway, so I'll look at this, and this is the answer to the question before. This is an even function, symmetric around the y-axis. So that means all the B sub n's are going to be 0. And I meant to confirm that, but we didn't. All right, but now Mathematica has confirmed for us that all of these B sub n's are 0. And then I'm going to take this mess, plug it in here, and say, what does this simplify when I have integers? And it simplifies down to this. And if you stare at this, that's the same thing as what I have written over here. Okay. Then plug that in and write this out. We'll just do the first of the Fourier. It's a cosine wave, which models well that triangular wave. And then it very quickly converges nicely. Oh, sorry. Remember that half of these things are 0. So when I go from 3 to 4, nothing happens. So I'm going to go from 3 to 5. And then if I go up to 15, it'll look really, really good. I don't see any of that Gibbs phenomenon this time because it's not a discontinuous function. It models it really, really well. Okay, so now we're going to talk about the homework. I'm going to jump to another video just to talk about that. That way you can have them in different places. So stopping this recording. Hope that all makes sense.